So we will talk here about the equations of motion. The equations of motion are important. They tell us what happens with the flow. I have an airplane. It tells me if I have an injet, let's say, it tells me that how much mass is going inside here, how much mass should go outside there. It would tell me what happens with all my fluid particles around this. And when I design this, there are two ways I can do it. I can think about the small particle that's moving along this and just think that you stand on top of the particle and you move with the particle. Or you may say, I'm going to stay still in a space of time. I'm going to watch what the particle does. There are two different ways to analyze the whole thing. One has benefits over the other, and one brings more complexity as well when we are doing the analysis. So what we're going to do here is we will talk about the theory or equations of motion. And to begin this, there are three things that three type of equations that are very, very important that we will be using. Okay, so the fluid dynamic behavior is based on three major concepts. The first one is based on mass is conserved. Okay, so this is nothing else and also known as the continuity equation, and it comes from that. So the mass cannot be created, nor can it be destroyed, right? We know that from Newton's laws. So, and then momentum is also conserved. And this comes from Newton's second law. Okay. And the third one is the energy is conserved. This is nothing else than the first law of thermodynamics. Okay, and I'm staying ahead of myself, and for a very specialized case, we're going to show that from here is where you're going to get the Bernoulli equation. Okay, the Bernoulli's equation that we will be using a lot. So before we move on, let me fix some ideas in space. First of all, when we are doing a study, there are two types of ways that I can do my control value. As I just told you, one way is let me stay fixed in space, okay, and let me watch what happens to the flow as it moves along. The other method is let me stay on top of the fluid, let me move with the fluid, so my control volume is moving with the fluid. This is the Lagrangian method, this is the Allurian method. Okay, and they have their purposes, right? So if I'm working the Allurian method, it's a different type of integral form, especially if we work at a microscopic level. That's what's important. If I'm staying on top of the particles, I'm moving with the particle itself, typically we have a differential equation. We don't have an integral form of the equation. However, it is possible to express this differential equation also in terms of integral form, which is not the same as this integral form. Okay, and this is also at the microscopic level. So, to better understand a few things here, let's think a little bit about what happens in each one of these perspectives. Okay, first perspective we have is the Lagrangian perspective. Perspective. And remember, this is the particle perspective. So we are staying on the particle, we're seeing what's happening in the particle. So in this case, this is the flow as seen moving with the fluid. Fluid material. Okay. Number two, what we do is we monitor what happens at the fluid. We monitor the fluid particle. We monitor a given mass element of the fluid. Okay. So when we say this, we are basically saying the following. And then assume that I have a given mass and I have a given mass. We know the masses have to be equal. But what we are saying is we're going to stay at that one particle that's right there. Okay. And we have the same. Let me change the color so you can better see it. So I have a particle here and I have the same particle coming on this side. Okay. So assume that we got all the streamlines, right? So this is like a stream tube, if you would, that is moving in this direction. So what we know that what you could say here is that my x is actually a function of my initial coordinates where everything began. Why? Because, and the same thing for y. Why? Because I am moving along with the particle. So therefore, everything that happens is going to happen as I vary with x, y, and z. And that's going to change in every time step that I actually do my analysis. Okay? Okay. And you can see that sometimes it's not very convenient to use this method. Sometimes it is, so it's all going to depend. So the other case scenario that we have what we call the Allurian perspective. Okay, so the Allurian perspective is the flow seen from a fixed coordinate system. So now the coordinate is not moving, the fluid is moving. So we want to monitor a given element as fluid flows in and out. Okay, so basically you have a fluid that comes inside and you have a fluid that goes outside. Okay, so that's what it consists in. Okay, so that's the whole idea behind this. Now, the one thing that's very important when we are doing this fluid analysis is something we call substantial derivative. And we already use this in a way, but here we're going to give you a formal definition of what this substantial derivative really is. So to better understand this, let's consider a fixed coordinate system. Let's consider we have this fixed coordinate system. And this coordinate system, we are starting here at t sub 0. And then I have this at t plus delta t. This is at t plus delta d3, and so on and so forth, right? and then my fluid is going in this direction. It's all moving in this direction, but my particle here is basically moving from here to my time t. Okay, this is t, this is t sub 0. This is the beginning point. This is where everything starts. And then there's a distance from here to here of s. There's a distance from here to here that will be s plus delta s. Then this will be s plus delta s2, and so on and so forth, right? And I can keep on going. And one thing that you keep in mind is that delta s is nothing else than your velocity times delta t, if you remember your definition of velocity. And when I say v here, v is nothing else than the magnitude of your vector v. Okay, so we call this speed because it's the magnitude. So the big question here we have is, let's consider a quantity. Consider some point quantity with the letter q. And let's say this quantity is a function of x, y, z, and t. This can be anything. It can be a vector. It can be a scalar. Okay, that really doesn't matter. The question is, how does q vary with time? Okay, so if we want to do this, first of all, just note this, that q in general can be a function of time. Okay, so we are basically saying that each one of these each one of these guys are a function of time, right? So x, y, and z, they're all implicit functions of time, and so is this a function of time. So what we are trying to do is we are trying to track the particles with time. Okay, that's what we are really trying to do. And we also know that I have a velocity vector that's actually is going to have these velocity components in the more general sense. So what I want to know is what would be my big Q, the total derivative with respect to t. So if I want to know what this is, now you know that this is all a function of x, but x is a function of time. If I'm taking this with respect to time, remember we have to use the chain rule. Okay, so the chain rule says partial of q respect to x, but then I also have x respect to t. Then I have partial of q respect to y, partial of y respect to time, plus partial of q respect to z, partial of z respect to time, plus partial of q respect to time, because this is the other constant I have here. Now, if you realize this is nothing else than your velocity vector u, this is nothing else velocity vector v, this is nothing else velocity vector component, sorry, w. Okay, so we can rewrite this whole thing in the following form, in the most general form, as v dot delta q plus partial of q respect to t. So in other words, I can take the substantial derivative of anything I want as follows. Okay? So when I do this, there is absolutely, so what really happens here is there are a couple definitions here. This is what we are going to call the substantial derivative. Okay? This is what we're going to call the convective derivative. And this is what we should call the local derivative. Okay? So these concepts are important in our analysis to understand this. So that means it doesn't matter what I give you, you can always use this expression to find your total derivative in your problem.